The Committee on Science, Space, and Technology will come to order. With that objection, the Chair is authorized to declare recesses of the committee at any time. Welcome to today's hearing, which is called Astrobiology and the Search for Life Beyond Earth in the Next Decade. Let me make a couple of announcements. One is an explanation, and that is to say that we expect more members shortly, but at least on the Republican side, all of our members are in a Republican conference that I left early in order to start on time here, but other members will be arriving shortly, and the same may be true of our colleagues on the other side of the aisle as well. We have a new member of the Science, Space, and Technology Committee, and I would like to introduce him. He is Darren LaHood, the first member to my left, whose father I served with in Congress some years ago. Darren LaHood represents a district in Illinois. He's a former state senator, or serving as a state senator when he was elected to Congress. Before that, he was both a state and federal prosecutor. So we welcome his many talents to the committee. He is going to be serving on two subcommittees, Research and Technology and Oversight, where he will be bringing all those legal skills to bear. And so we are pleased to have him join us today and permanently on this committee. And welcome, Darren, to you.
Thank you, Chairman.
I'm going to recognize myself for an opening statement, and then I'll recognize the ranking member. Edwin Hubble once said, "Equipped with his five senses, man explores the universe around him and calls the adventure science." There are few greater adventures than the search for life beyond Earth. When the Hubble Space Telescope was launched in 1990, planets around other stars had not yet been discovered. The only planets we knew were those that orbited our sun. Since 1995, however, when the first extrasolar planet was detected, the rate of discovery of new exoplanets and external solar systems has been truly remarkable. Today, with the Kepler telescope, we have found nearly 2,000 confirmed planets that orbit around other stars in our galaxy. Of these, 306 lie within the habitable zone of the stars they orbit, where water could exist, and 14 are almost the size of the Earth. Whether life exists beyond Earth, and if so, how humans can detect it, is a critical question. If definitive evidence of life is found, it may be the most significant scientific discovery in human history. The search for life in the universe is a priority of NASA and the U.S. scientific community. Seeking habitable planets is one of the three scientific objectives of the 2010 National Research Council Decadal Survey on Astronomy and Astrophysics. The United States pioneered the field of astrobiology and continues to lead the world in this type of research. Since the space program began, NASA has explored the cosmos for life beyond Earth and has conducted scientific research that investigates this possibility. NASA's astrobiology program continues these scientific endeavors to improve our understanding of biological, planetary, and cosmic phenomena. Just yesterday, NASA announced that it identified flowing briny water on Mars. This past April, NASA's chief scientist, Dr. Ellen Stofan, made global headlines with her prediction that, quote, "We are going to have strong indications of life beyond Earth in the next decade and definitive evidence within the next 20 to 30 years," end quote. And I'm glad that Dr. Stofan has joined us today. Within our solar system, the question of whether life exists or existed on Mars continues to capture the public imagination. In the past year, NASA's Curiosity rover made several major scientific discoveries relevant to the search for life on Mars. Curiosity measured a spike in levels of the organic chemical methane in the local atmosphere of its research site. It also detected other organic molecules in drill samples from a mudstone that once sat at the bottom of a lake. And Jupiter's moon, Europa, shows strong evidence of an ocean of liquid water beneath its surface, which could host conditions favorable to some form of life. NASA selected 9 science instruments for a future mission to Europa. 2 of them are from the Southwest Research Institute in San Antonio and 1 from the University of Texas in Austin. These instruments will help scientists investigate the chemical makeup of Europa's potentially habitable environment. Last July, astronomers, with the help of the Kepler Space Telescope, confirmed the discovery of Kepler 452b, the first near-Earth-sized planet in the habitable zone around a Sun-like star. This discovery marks another milestone in the journey to find another Earth. The Transiting Exoplanet Survey Satellite, which will launch in 2017, and the James Webb Space Telescope, which will begin in 2018, will help scientists discover more planets with potential biosignatures in their atmospheres, such as evidence of oxygen and methane gas. Around the world, a relatively small number of astronomers monitor radio and optical emissions throughout the universe. They try to filter out the cosmic noise and interference of satellites and spacecraft to find anomalies that could represent life. The search for life beyond Earth also inspires a new generation of explorers. It motivates students to study math, science, engineering, and computer science. Just a few months ago, astronomers confirmed that Tom Wag, a 15-year-old student, discovered exoplanet WASP-142b, which orbits a star approximately 1,000 light-years away in the constellation Hydra. It is in our human nature to seek out the unknown and to discover the universe around us. The stars compel us to look upward and lead us from this world to another. Many Americans often gaze into the beauty of the night sky in awe. Some may wonder if there is life beyond our pale blue dot. I thank our witnesses and look forward to hearing their testimony today, and particularly about recent developments in the field of astrobiology and the search for life. And now we'll recognize the gentlewoman from Texas, Eddie Bernice Johnson, the ranking member, for her opening statement.
Thank you very much, Mr. Chairman, and good morning. And let me welcome our distinguished panel of witnesses today. I do look forward to your testimony. I want to welcome Ms. LaHood to the committee and simply say that the first week of this month, I visited the Curiosity team in France, and the excitement is beyond measure. Administrator Bolden stated in the preface of NASA's strategic plan that when we explore the solar system and the universe, we gain knowledge about the dynamics of the sun and the planetary system and whether we are alone. With respect to the question of whether we are alone, in search for life beyond Earth is a topic this committee has devoted a lot of attention to over the past 2 years. I don't know if we plan on taking up life somewhere else. I don't know where our chairman wants to go, but I'm interested in following him. I understand that the purpose of today's hearing is to get another update on that topic. It is my hope that our witnesses will also take some time to discuss how their research activities can be used to help foster excitement in our young people and spur them to pursue careers in science, technology, engineering, and math. That's important because these young people are the future science and technological leaders and innovators who will be critical to our nation's growth and progress going forward. While it's exciting to search for intelligent life elsewhere in the universe, I hope we don't neglect nurturing the intelligent life we have right here in our country. As a final note, I want to recognize that this is a return visit by Dr. Lunine. 1 year ago, he and Governor Mitch McDaniels testified before the committee on their National Research Council's panel's report entitled Pathways to Exploration, a Review of the Future of Human Exploration, and that was completed pursuant to NASA Authorization Act of 2010. I highly recommend that our newer colleagues on the committee and in the rest of the Congress as a whole, for that matter, read this report, as I found it to be objective in its endorsement of the goal of sending humans to Mars and thoughtful in its recommendations for an exploration program to send humans to the surface of Mars. A central goal established by this committee in the House-passed NASA Authorization Act of 2015. And with that, I again want to thank our witnesses, and I yield back.
Okay. I thank the ranking member for those nice comments. Let me introduce our witnesses. Our first witness is Dr. Ellen Stofan, NASA's chief scientist. She serves as principal advisor to NASA Administrator Charles Bolden on the agency's science programs and science-related strategic planning and investments. This is Dr. Stofan's second term at NASA, as she recently held a number of senior scientist positions at the Jet Propulsion Laboratory. Dr. Stofan is a recipient of the Presidential Early Career Award for Scientists and Engineers. She earned her bachelor's degree from William & Mary and her master's and doctorate degrees in geological sciences from Brown University. Our second witness today is Dr. Jonathan Lunine, the director of the Cornell Center for Astrophysics and Planetary Science at Cornell University, where he specializes in astrobiology. Dr. Lunine has extensive experience in the search for life on other planets. He worked as an interdisciplinary scientist on the Cassini mission, which showed that one of Saturn's moons may host microbial life, and on the James Webb Space Telescope, which will study the origins of life in the near future. Dr. Lunine received his bachelor's degree in physics and astronomy from the University of Rochester and his master's and PhD in planetary science from the California Institute of Technology. Our third witness is Dr. Jacob Bean, assistant professor of astronomy and astrophysics at the University of Chicago. Dr. Bean also is the leader of the Bean Exoplanet Group, which uses telescopes to detect and characterize exoplanets. Dr. Bean's work has used the Hubble and Spitzer telescopes to make breakthroughs in astrobiology, which include the measurement of the first spectrum of a super-Earth planet. Dr. Bean also develops new instruments for exoplanet detection and characterization and is helping to design the giant Magellan telescope, which will soon be the world's largest telescope. Dr. Bean received his undergraduate degree in physics from the Georgia Institute of Technology and his PhD in astronomy from the University of Texas in Austin. Our final witness today is Dr. Andrew Simeon. Dr. Simeon is an astrophysicist at the University of California, Berkeley, and serves as director of the UC Berkeley Center for Search for Extraterrestrial Intelligence Research. Dr. Simeon's research interests include studies of time-variable celestial phenomena, astronomical instrumentation, and SETI. And Dr. Simeon also is a leader of the Breakthrough Listen Initiative, a 10-year, $100 million initiative to search for extraterrestrial life that is possibly the most comprehensive search for alien communications to date. Dr. Simeon received his PhD in astrophysics from the University of California at Berkeley. We welcome you all. You're clearly experts in the field. And Dr. Stofan, will you begin?
Thank you. I'm pleased to appear before the committee to discuss astrobiology and the search for life beyond Earth. If I could have the first slide, please. NASA's science missions are providing strong evidence of possible habitable environments beyond Earth. With future technology and instruments currently under development, we will explore the solar system and beyond, and could indeed, perhaps in as little as 10 to 20 years, discover some form of life, past or present. Our search is making amazing progress. When I was a PhD student, scientists certainly suspected that planets might be commonplace in the universe, but we had not found evidence of a single one. 20 years ago, we found the first evidence of such a planet, and today, thanks to NASA's space missions and ground-based telescopes, we have identified nearly 5,000 planets orbiting other stars, and we now believe that the vast majority of stars in the universe have planets around them. In July, the Kepler mission confirmed the first near-Earth-sized planet in the habitable zone around a Sun-like star, Kepler 452b. On Mars, a series of NASA missions culminating in the Curiosity rover, which touched down in Gale Crater nearly 3 years ago, have allowed us to make fundamental discoveries. Next slide. We now know that Mars was once a water world, much like Earth, with clouds and a water cycle, and indeed some running water currently on the surface. For hundreds of millions of years, about half of the northern hemisphere of Mars had an ocean, possibly a mile deep in places. Indeed, we now know that we live in a soggy solar system, and undoubtedly in a soggy universe. For instance, Jupiter lies outside the habitable zone, and we would expect water there to be frozen. Yet we now have evidence of liquid oceans on 3 moons of Jupiter under the icy crusts of those worlds. And using the Hubble and Spitzer space telescopes, we have found signs of water in the atmospheres of planets around other stars. So what lies ahead in the next decade of exploration? I'd like to describe just some of the highlights. Life as we know it requires water, liquid water, that's been stable on the surface of a planet for a very long time. That's why Mars is our primary destination in the search for life in our solar system. The Mars 2020 rover mission will study Martian rocks and soils to understand past habitable conditions on Mars and to seek signs of ancient microbial life. If we do find evidence of life on Mars, it will likely be fossilized microorganisms preserved in the rock layers. The Mars 2020 rover will begin the search, but as a field geologist, I can tell you it's going to be hard to find. That's why I believe it will take human explorers who can move quickly and make intuitive decisions on their feet to really identify it, and in doing so, inspire that next generation of explorers. Over the next decade, our journey to Mars involves the development of a commercial crew capability for low Earth orbit, the Space Launch System, and Orion to go beyond low Earth orbit, and an asteroid redirect mission. Beyond Mars, the President's FY 2016 budget request supports the formulation and development of a new mission to the Jovian moon Europa. If I could have the next slide. We estimate that Europa has twice as much water as the Earth's oceans, and Hubble has observed plumes of water at one of Europa's poles. A Europa mission could potentially, among other things, analyze these water plumes to determine the composition of those oceans. Beyond our solar system, there are countless other worlds that could harbor life. In 2017, NASA will launch the Transiting Exoplanet Survey Satellite to look for rocky planets near the habitable zone of the closest stars. Next slide. We will then use the James Webb Space Telescope to analyze the atmospheres of some of these planets. The President's FY 2016 budget request also supports the pre-formulation of a wide-field infrared survey telescope with the capability of directly imaging planets around the nearest stars and analyzing their atmospheres. Since Earth remains, for now, the only instance of an inhabited planet, the search for life also requires that we further develop our understanding of life on Earth. Through our research here, we have learned that life is tough, tenacious, metabolically diverse, and highly adaptable to local environmental conditions. Astrobiologists have discovered life in numerous extreme environments and in extraordinary forms, from bacteria that consume chemicals that would be toxic to most other life, to microbes that live under high levels of radiation. Perhaps even more interesting is the possibility that life could exist in the absence of liquid water. That's why scientists are interested in exploring some of the more unusual places in our solar system and beyond, such as Saturn's moon Titan, where it rains liquid methane and ethane. Could such an environment harbor life? We don't know yet. Ultimately, of course, the search for life is a cross-cutting theme in all of NASA's space science endeavors, bringing together research in astrophysics, earth science, heliophysics, and planetary science. Astrobiology is guided by a community-constructed roadmap generated about every 5 years, with the next roadmap slated for release later this year. In addition, in April, NASA announced the formation of an initiative dedicated to the search for life on planets outside of our solar system. The Nexus for Exoplanet System Science is an interdisciplinary effort that connects top research teams and provides a synthesized approach in the search for planets with the greatest potential for harboring life. From research to our knowledge of where to go and what to look for, to the capabilities of finding it both within our solar system and beyond, we are making great discoveries. Thank you for the opportunity to testify today.
Thank you, Dr. Stofan. Dr. Lunine.
Thank you, Chairman Smith, Ranking Member Johnson, and members of the committee. Thank you for the opportunity to present my views on the search for life beyond Earth. These views are my own, and they come from 30 years of working in the field of planetary science at various institutions in the U.S. and abroad. One of the most important outcomes of the last 2 decades of solar system exploration is the identification of 4 bodies in our solar system that appear capable of harboring life. These bodies possess a particular set of characteristics that make them the best leads in the search for life beyond the Earth. If I could have the first slide, the first of these bodies is Mars. In its first billion years, Mars had abundant liquid water, stabilized and protected by a much denser atmosphere than the tenuous shell we see today. During this time, life might have begun, survived for a while on the surface, and then was extinguished or retreated underground as the atmosphere was lost. If I could have the second slide, the second of these objects is Jupiter's moon, Europa. It's a body the size of our own moon. It has a very large saltwater ocean, twice the water that we have in our own ocean. This ocean is in contact with a rocky core and abundant sources of energy. As yet, we don't know whether organic molecules exist inside of this ocean, but we strongly suspect that they are there. Equally important, we don't know how far below Europa's surface the ocean lies. Knowing that will allow a strategy to be formulated for searching for life there. Next slide is Titan, a Saturnian moon that's larger than the planet Mercury and the only moon in our solar system to host a dense atmosphere of nitrogen and methane. Cassini and its lander Huygens have revealed methane clouds, rain, gullies, river valleys, and methane-ethane seas. And so we cannot resist asking whether some biochemically novel form of life might have arisen in this exotic, frigid environment. Titan is a test for the universality of life as an outcome of cosmic evolution. To quote the historian Stephen Pine, what the Galapagos Islands did for the theory of evolution by natural selection, Titan might do for exobiology. Finally, next slide, Enceladus has surprised us. This small Saturnian moon has a large plume of material emanating from a series of fractures in its south polar region. Make a list of the requirements for terrestrial-type life: liquid water, organics, minerals, energy, chemical gradients, and Cassini has found evidence for all of them in the plume of Enceladus. So how do we actually find the signs of life in these bodies? The evidence will not be entire living organisms. Much more likely is that we will detect signatures that indicate that life is at work or was at work in these environments. In contrast to non-biological processes, biology is built from a very limited, selected set of molecules. And so if we can recognize patterns in the makeup of organic molecules and their isotopes, we then have strong evidence of biology at work. At Mars, finding sources of methane and measuring their isotopes is one way to get at this question. Another is to seek well-preserved organic materials in the soil to see if they record the signatures of biology. And the Mars 2020 rover will do the heavy lifting here. For Europa, the Europa mission now in development will provide the essential information needed to decide, among other things, whether organics and water are welling up through the cracks on the surface and whether plumes exist and can be measured. Doing this mission, doing it now, is absolutely crucial to any general strategy for the search for life. For Titan, the search should target one of the great methane-ethane seas by dropping a capsule capable of floating across the surface. We don't know what kind of biochemistry we're looking for here, and so a generalized search for patterns in molecular structures and abundances that indicate deviation from abiotic chemistry is appropriate. And finally, Enceladus provides us with the most straightforward way to look for life. Merely flying through the plume of Enceladus, as Cassini has done multiple times, with modern instrumentation intended to detect the signatures of life, is sufficient to do the search. The long flight times in the outer solar system, in particular, dictate that planning for missions to Enceladus, Europa, and Titan must begin now and must be pursued with vigor if they're to happen in the next 2 decades. It is remarkable that we have found 4 destinations in our own solar system where life may actually exist or have existed for quite some time in the past. And now is the time to actually go search for that life. Thank you.
Thank you, Dr. Lunine and Dr. Bean.
Mr. Chairman and members of the committee, good morning and thank you for the opportunity to serve as a witness for this important hearing. My testimony today will be focused on the topic of exoplanet spectroscopy in the context of the search for life beyond Earth. The main point I want to convey is that an expanded exoplanet exploration program with a flagship exoplanet spectroscopy space telescope as its centerpiece could answer one of humanity's most fundamental questions: is there life elsewhere in the universe? Extrasolar planets, or exoplanets for short, are planets outside our solar system that orbit stars other than our sun. This year marks just the 20th anniversary of the first detection of an exoplanet orbiting a sun-like star, but progress in the field has been rapid in the intervening years. In particular, the launch of NASA's Kepler telescope in 2009 has revolutionized the field. The Kepler mission has advanced to the point that it is now focused on finding Earth-sized planets orbiting their host stars in the so-called habitable zone, which is the distance at which the temperature on the surface of a terrestrial planet could be right for liquid water to be present. A handful of Earth-sized, habitable zone exoplanets have been found over the last few years. These discoveries have grabbed the attention of the scientific community and the public because they suggest that Earth-like planets may exist around relatively nearby stars, and that we therefore have it within our grasp to search for life on other worlds in our lifetimes. The next step towards determining if there are any truly habitable planets, or even inhabited planets, is to study the atmospheres of candidate worlds using the technique of astronomical spectroscopy. Planetary atmospheres are a key factor controlling the habitability of a planet because they are reservoirs of biogenic elements and regulators of planetary surface conditions. Furthermore, planetary atmospheres can be influenced by interactions with the biosphere, and thus may be a marker of life itself, absent direct observation or communication. Astronomers have made progress revealing the nature of the atmospheres of hot, gas giant type exoplanets using the Hubble and Spitzer space telescopes and the ground-based Keck and Gemini telescopes. These investigations have yielded constraints on the abundances of key chemical species, the identification of clouds, and the determinations of temperature maps. Astronomers eagerly await the launch of the James Webb Space Telescope in 2018. Among its many new important capabilities, the Webb telescope will dramatically extend the reach of exoplanet spectroscopy. It may even have the capability to determine the presence of major molecules like water and carbon dioxide and measure the temperatures of Earth-sized exoplanet atmospheres. However, Webb will be hard-pressed to detect evidence for life, only made possible with fortuitous planets, extraordinary performance of the instrument, and large amounts of biosignature gases in the planets themselves. A flagship space telescope with next-generation optics will likely be needed to detect evidence for life on other Earth-like exoplanets. The astrophysics community is currently ramping up for a decadal survey that will prioritize large space missions to follow the Webb telescope. At the wise urging of NASA leadership, the community is currently developing concepts for telescopes that could take spectra of Earth-like exoplanets in preparation for the decadal selection process. The top priority space telescope from the previous decadal survey, currently dubbed W1st AFTA, will have capabilities that lay a foundation for a future Life Finder telescope. One of the science goals of the W1st AFTA mission is to obtain improved statistics on the frequency of potentially habitable planets. In addition, NASA is currently considering including an exoplanet spectrometer on the telescope. This instrument would not have the capability to make measurements for Earth-like planets, but it would advance the science and technology in that direction. As a final point, it is important to keep in mind that a future Life Finder mission cannot be a success in the absence of other projects. The need for comprehensive knowledge to confront the question of life on other planets is why I think that ultimately an expanded program in exoplanet exploration would be the best way forward. Although a flagship space telescope would be the crown jewel, this program should be driven by the question of life rather than the construction of a single facility. It would take courage and perseverance by scientists, government leaders, and the public all working together to act on this vision and see it through. But our ability to rise to this kind of challenge is what makes America exceptional. From the Apollo program, through the Voyager, Hubble, and Mars rover programs, with the recent stunning success of the New Horizons mission to Pluto, and today with the launch of the Webb telescope just a few years away, our country leads the way in projects that are lasting milestones of space exploration. The search for life beyond our planet represents the next great space exploration challenge that would continue this legacy. Mr. Chairman and members of the committee, thank you again for the opportunity to be here as a witness, and I would be happy to take questions.
Thank you, Dr. Bean and Dr. Simeon.
Chairman Smith, Ranking Member Johnson, and members of the committee, thank you for the opportunity to testify today. Searches for extraterrestrial intelligence, SETI experiments, seek to determine the distribution of advanced life in the universe through detecting the presence of technology, usually by searching for electromagnetic radiation from communication technology, but also by searching for evidence of large-scale energy usage or interstellar propulsion. Technology is thus used as a proxy for intelligence. If an advanced technology exists, so too does the advanced life that created it. We know of no way to directly detect intelligent life, but if other intelligent life exists and possesses a technological capability similar to our own, we could detect their technology using the techniques of modern astronomy. Large radio telescopes, such as the Green Bank Telescope in West Virginia and the Arecibo Observatory in Puerto Rico, are superb facilities for a wide range of astronomy. including pulsar studies that test Einstein's theory of general relativity, mapping the gas in nearby galaxies, and probing the earliest epochs of the universe. In addition, these facilities are among the world's best at searching for the faint whispers of distant technologies. A variety of radio SETI experiments are underway at both the Green Bank Telescope and the Arecibo Observatory, including some that allow us to observe in parallel with other astronomers without interfering with their work, a technique we call piggyback observing. Several other U.S. and international radio telescopes are also currently being used for radio SETI, including the private Allen Telescope Array in Northern California, the Low Frequency Array in Europe, and the Murchison Wide Field Array in Australia. Many radio SETI searches are taking advantage of the wealth of new information on our galaxy's exoplanet population, now being revealed by missions such as NASA's Kepler spacecraft. In a very exciting new project, a group based at the University of California, San Diego, are using the Lick Observatory near San Jose to conduct a search for pulsed lasers in the near infrared, wavelengths just a hair longer than optical light, but much better at penetrating the dusty space between the stars. These SETI experiments are funded by a combination of government and private sources, including notable contributions from the John Templeton Foundation. Ensuring that facilities like the Green Bank Telescope, Arecibo, and the Lick and Keck observatories continue to exist as world-class astronomical facilities is critical to their continued use in SETI experiments. One of the most exciting prospects for SETI in the next decade is the Breakthrough Listen initiative, a $100 million 10-year effort funded by the Breakthrough Prize Foundation that will conduct the most sensitive, comprehensive, and intensive search for advanced intelligent life on other worlds ever performed. I have an animation I would like to show you illustrating some components of Breakthrough Listen. Here we see the Milky Way galaxy, a galaxy that we now know hosts tens of billions of planets in the habitable zone of their star, planets that might have liquid water on their surface. If intelligent life arose on some of these planets and developed radio technology, the emissions from their technology would proceed at the speed of light out into the Milky Way. But for how long? Life may arise, it may develop intelligence, and finally a communicative technology, but that final stage may only last for a few thousand years. But the evidence of their technology, the bubble of their electromagnetic radiation, will continue to propagate throughout the galaxy and could eventually be detectable at the Earth. With Breakthrough Listen, we will conduct deep observations for these types of emissions from 1 million of the nearest stars to the Earth that will be at least 10 times more sensitive than ever performed. These observations will cover at least 5 times more of the radio spectrum than any previous experiment. We will conduct these observations using the Green Bank Telescope in West Virginia, as well as the Parkes Radio Telescope in Australia. It is undoubtable that the next decade will be an incredibly exciting time for astrobiology. Data provided by missions like the Transiting Exoplanet Survey Satellite and the James Webb Space Telescope virtually guarantee dramatic new insights into exoplanet science, including identifying and characterizing some of the nearest exoplanets to the Earth. At the same time, we will continue to learn more about the development of life on Earth and the potential for life elsewhere in our own solar system. If history is any guide, these discoveries will only heighten our imagination about the possibilities for advanced life elsewhere in the universe. Thank you.
Yeah. Thank you, Dr. Simeon. As you might guess, we all have thousands of questions, and we're somewhat limited in our time by 5 minutes. But Dr. Stofan, I'd like to address a couple of questions to you. One, I'm absolutely astounded by the announcement by NASA that briny water may be on the surface of Mars. Is that the case? When the Mars Curiosity rover reported no evidence of water, I thought that was the end of it. But if we have this water on the surface of Mars, why is it we do not have any photographs of that water?
Indeed, the new results that we just got show that the recurring slope lineae, these features that are on the sides of some craters on slopes, that seasonally, over time, it seems that water melts.
Right.
Briny water carries those materials down slope, and we've finally been able to put all the evidence together, including chemical observations, to say, okay, that's really what's forming these things, which we're incredibly excited about. The problem is these features are very transient. there's not a whole lot of water that's carrying those salts, and so it's very hard to see with the resolution of spacecraft that we see. But again, we can certainly trace the chemical signatures. We also, at the Phoenix landing site, were able to see the evidence of liquid water, including a little droplet on the spacecraft. So, you know, water is there on Mars. It's not in huge abundance right near the surface, but we know it's at the poles. We know it's
Could be
under
frozen at the poles. When will we have evidence of liquid water? Anytime soon?
I'm afraid I can't answer exactly when we'll have. We feel that the evidence we showed yesterday is certainly good evidence of liquid water, but you have to understand that those water, when it's flowing on the surface, it's very, very hard to detect.
Okay, thank you. Next question is, where are we, in your opinion, most likely to detect any form of life, even if it's bacteria or microbes or whatever? Is it going to be Mars? Is it going to be Europa? Is it going to be an exoplanet? Is it going to be some technological communication? Where do you think the best prospects lie?
Well, I certainly believe that it's going to be Mars. And I think, as you heard from me and you heard from Dr. Lenine, we're very optimistic about the 2020 rover and its potential for looking for signs for ancient microbial life. Now, again, that's not the most exciting in a lot of people's terms to find fossilized microbes, but that's, or the signatures that those microbes existed. But I'm really optimistic. But again, I think it's going to take humans on the surface of Mars to really get at the definitive evidence to study that liquid water that we want to see.
Okay, thank you, Dr. Stolpat. Dr. Lenine, how would you rank the various, let me start again. You mentioned 4 locations, Mars, Europa, Titan, and Saturn, one of Saturn's moons, and Enceladus. Was that in order of likelihood, or do you have a preference or a prediction as to where we might most likely find evidence of some form of life?
Well, that was actually in order moving outward from the sun. So there was no implied order. You know, the question is whether in any environment that can support life, does life actually begin? Does it form? And I don't know the answer to that, and no one else does. And that's why, in my view, we need to look at all of these bodies where there is very strong evidence, compelling evidence of what's called a habitable environment where life could actually be sustained.
And when we find out what the thickness of the ice is on Europa, that's the time to send a probe there, I gather.
Yes, there's a lot of groundwork that has to be done on Europa. We don't know if there are organic molecules. The Europa mission will tell us whether there are fresh organics in the cracks. If there are, that would be the place to go.
Let's go. Thank you. Dr. Bean, when do you think we will have the capability of detecting biosignatures in the atmospheres of exoplanets?
Yeah, so as I mentioned, I think the James Webb Space Telescope, which is planned to launch in 2018, will be our first chance to do that. If we get lucky and we find the kinds of planets that are orbiting very nearby stars, then we may be able to search for biosignature gases.
With James Webb?
Yes.
And not before? You think it's going to take?
Definitely not before.
Okay. I'm going to ask you also, what do you think the odds are of actually finding a biosignature, say, in the next 10 years? Well, let me ask you, likely or unlikely?
I'd say that's unlikely, but we're optimistic that we can take important steps towards doing that over the next 10 years.
Okay. Thank you, Dr. I was hoping you'd be a little bit more optimistic than that, but if you want to give a 1 out of 3, 1 out of 4, what would you say?
1 out of 5.
1 out of 5. That's better than otherwise. Okay. Thank you, Dr. And Dr. Simeon, last question for you. Could you briefly tell us the advantages and disadvantages of radio and optical astronomy? I know we're trying both. You seem to focus a little bit more on radio in your comments, but there's advantages and disadvantages to both. And do you have a preference or not? And if so, what are the advantages and disadvantages?
Yeah, I think you're absolutely right that historically SETI has concentrated on the radio portion of the electromagnetic spectrum. But as we've developed technology on Earth that allows us to communicate at optical wavelengths, we've moved some of our efforts in SETI to those wavelengths as well. The truth is that we don't know what part of the electromagnetic spectrum we might eventually receive some signal or some evidence of a technological civilization elsewhere. So it behooves us to search as much of that spectrum as we can. and that's why we focus on both the radio and the optical.
Okay, thank you, Dr. Simeon. My time has expired, but Dr. Bean, just a quick comment. You know that 20% is actually pretty high considering how historic that would be, and I think we all would agree it might be the most interesting news in, say, the last 100 years. So that 20% is something I think is not insignificant, so appreciate your comments. The ranking member, the gentlewoman from Texas, is recognized for her questions. And let me say, going back to her opening statement, that it's not often that the chairman hears the ranking member say she's going to follow the chairman. So I just wanted to...
If you go to Mars.
All yours.
Thank you very much, Mr. Chairman. Dr. Levine, today we are speaking primarily about astrobiology that can be carried out robotically. However, humans will one day return to deep space and carry out scientific exploration on bodies such as Mars. To that end, it has been over a year since the National Academies released the Pathways to Exploration study, which you co-authored. That report found that the horizon goal for human space exploration is Mars, and as you may know, this committee agrees with that. Has NASA been in discussions with you on the results of that report? And if so, what is the status of the response of that report, and how can this committee be helpful?
Well, the NASA Advisory Committee did actually have a session at one of their meetings on the subject of our report, and one of our committee members, Mary Lynn Dittmar, was there and had a dialogue with the committee and also folks from NASA, including Bill Gerstenmaier. So I think there's some dialogue and thinking going on. I look forward to having more dialogue with NASA on the report. I think it's still very fresh and has a lot to contribute to the question of how and when humans will move beyond low Earth orbit. And so I look forward to that dialogue.
Good. In your view, what, if any, of the issues does this committee and the Congress need to address?
In the context of that report?
Yes.
Well, you know, to quote from that report, we were concerned about the question of flight rates in the near term and the question of how the destinations or pathways might be chosen. And I still think those are the key operative elements in the recommendations from our report.
30 years from now, elementary school children will be leading the scientific exploration of the solar system and beyond. Our knowledge of other bodies near and far will have changed. Humans may have visited Mars, and even the two of us here in this committee won't be around. But life beyond Earth may have been detected by then. So I would like to ask all the panel members, as we think about where we are today and where we might be 30 years from now, is there anything that Congress should be considering to ensure that today's school children are well equipped to lead a new era that can include knowledge of life beyond Earth?
I'm a strong believer that NASA plays an incredibly important role in inspiring the next generation. And Charlie Bolden loves to say that everything we do at NASA is about STEM education. Every time we launch a rocket, every time we do something like encountering Pluto, we are inspiring the next generation to want to explore, to question why. And I would like to see NASA stay on the steady course we have been, with obviously this committee's support, to continue that exploration and move forward with moving humans out beyond low Earth orbit.
This nation has done some incredible things in exploring the solar system. One example that excites school kids is that the Cassini spacecraft can actually probe the large methane seas of Titan and determine their depths and their composition by sending radio signals through those seas as it flies by Titan. And so we're actually doing ocean exploration 1 billion miles away from the Earth, and that's only one example. School kids are fascinated by that. They want to be a part of it, and in order for them to be a part of it, we have to have continuity in exploration. We have to continue these wonderful missions so that there isn't effectively a generation-long gap in these discoveries.
To get back at Chairman Smith's earlier question, about putting a number on the chance of finding life. I want to emphasize that scientific process is a step-by-step deliberate process. And so being able to maintain, like Jonathan said, a continuity in funding these programs and continuing this deliberate approach, I think is extremely important.
I think the only thing that I have to add to what my other panel members have said is that the search for life, I think, has a particularly compelling aspect to it for young people. And I think to the extent that can be highlighted and taken advantage of to encourage more young people to enter careers into space and science and technology is wonderful.
Thank you very much. My time's expired.
Thank you, Ms. Johnson. The gentleman from Texas, Mr. Babin, the chairman of the Space Subcommittee, is recognized for his questions.
Yes, sir. Thank you, Mr. Chairman, and welcome all of you panelists. We appreciate it, and it's very, very fascinating to hear your testimony. In my district, Texas 36, the Johnson Space Center Astromaterials Curation Facility provides services for all returned planetary materials that do not require planetary protection laboratories. This facility has been in operation since the Apollo lunar samples were returned. In the next decades, we anticipate missions to collect samples from the Moon, from Mars, from comets, and from asteroids. Each of these new sample collections will require new curation laboratories, while the facilities for the older collections will require routine maintenance and upgrades. Samples to be returned from Mars pose even greater challenges due to special planetary protection requirements. Dr. Stoffen, what steps is NASA taking to upgrade its curation facilities and protect against the transfer of viable organisms from Earth to celestial bodies which may harbor life?
We have two different committees at NASA, certainly the Planetary Protection Group, where we take these issues extremely seriously, both for forward contamination of Mars and then backward contamination for when we eventually return samples to the Earth. So that's one aspect of where we are certainly doing research. We're doing testing of all our Mars spacecraft in the planetary protection area. We also have another group where we reach out into the community and bring experts in to advise us on our curation. I had the opportunity just this past year to tour the facility down at Johnson. It's extremely, it's an amazing facility. It's really fun to be able to go there and look at the Apollo lunar samples, the meteorites we've returned from Antarctica. And we take that facility, its preservation, and its eventual expansion as we move eventually towards bringing samples back from Mars. So we certainly work closely with the community to understand what is needed and to make sure we will eventually, when we do return samples from Mars, we will have a plan in place.
Thank you very much. And this is directed to everyone. What proportion of astrobiology research in the United States is funded directly or indirectly by NASA? Does anyone know? Okay.
No, we at NASA can certainly take that question for the record. I will say, I was just talking with someone a few weeks ago. I was at a conference at Ames Research Center where we were thinking about climate on extrasolar planets. And it's one of the reasons, as I mentioned in my testimony, that this whole area of astrobiology is a amazing one, and it's actually makes me think it'll be a little hard to pull that number out. We can certainly get you a number on the exact funding,
okay.
But when you're thinking about, for example, habitable conditions on stars, you have to be doing heliophysics to understand stars, the wind, that solar wind, the interior of the planet. Does it have a magnetosphere that then protects that atmosphere from being stripped away? The work we do here on Earth to understand extremophiles, planetary science, we're pulling from so many disciplines, which is, to me, what makes this area of science in particular so incredibly exciting and fruitful. It's truly interdisciplinary.
Absolutely. Okay, and also, what are the most important technological advancements that are needed to further astrobiology research, and what advancements should be our highest priority to continue this?
Well, I'll take one crack at this, and I don't want to prioritize these, but one in my area is to develop miniaturized instrumentation that can detect the chemical signs of life and also detect biological activity. The smaller the instruments, the easier it's going to be to send them to the planets.
From the standpoint of studying exoplanets, I talked in my testimony about building a very large space telescope as a flagship mission. That's a very high-tech thing that we have to do to take direct images of planets that we can take spectra from and look for the signatures of biosignature gases. That involves the construction of large space telescopes, rockets to put those telescopes into orbit, instrumentation to block the blinding glare of the stars those planets orbit, and perhaps even the manned spaceflight program to service those telescopes or even construct the telescopes in orbit.
Thank you.
I think in the search for extraterrestrial intelligence, the low-hanging fruit is very much digital signal processing technology. So improving our ability to process the very, very high data rate streams that are produced by radio telescopes and some optical telescopes, and also developing receiver technology for radio telescopes that allow us to use old facilities in new ways.
Right, thank you. And Mr. Chairman, I'll yield back the balance of my time. Thank you, panelists.
Thank you, Mr. Babin. The gentlewoman from Connecticut, Ms. Esty, is recognized for her questions.
Thank you, Mr. Chairman, and thank you, Ranking Member Johnson, for holding today's fascinating hearing, and thank you to all of you. I joined millions of Americans on Sunday night watching the blood moon and a blue moon earlier this year, and I have to tell you, in a district like mine in Connecticut, school children are incredibly inspired and excited by these developments, and many of us here on this panel share a commitment to STEM education, and so it's in part through that lens I would like to proceed with my questions. Congratulations, Dr. Stofan, an incredibly exciting announcement yesterday, and we look forward to understanding what that means, and as you can hear, we've already had questions today. Dr. Stofan, you spoke earlier about the need to have human exploration on Mars to really understand and to make those subtle intuitive judgments that are necessary. Do you anticipate that yesterday's announcement and the discovery preceding that changes in any way the priorities or the ordering of that, and help us understand in our role as decision makers on helping to set priorities that are keeping up with the developing science?
You know, I think one of the most exciting things about yesterday is the fact that we now know there's near-surface liquid water on Mars. And so this idea that Jonathan Lenine mentioned in his testimony of, you know, again, because of this length of time that we know that water was stable on Mars, that's what makes scientists think that Mars is the place where life maybe could have evolved, because not only did you have liquid water, but you had the time to allow the chemical reactions to take place. The exciting thing about knowing there's near-surface water is saying maybe there could still be life forms on Mars today, deep underground, several meters below ground, where the cosmic radiation that affects Mars would not affect them. But the idea that it's potentially accessible to be studied by, again, astronauts and laboratories on the surface of Mars. And again, as a field geologist, somebody who likes to go out in the field and crack open rocks, I just have this strong bias that it's going to take humans, laboratories, a lot of work. Because again, it's one thing if you're looking for something large. If you're looking for something small, it's going to take time and it's going to take effort. And that's why I think humans are so critical. And that's why NASA has chosen to be on this path. And I think the findings from yesterday convince us we're on the correct path.
Thank you, and I have to confess I have a son who did astrophysics and did exoplanet things, so I have a personal I know he has a personal interest in discovering if this manned mission is going to keep up with his fourth grade project from, you know, about 15 years ago. Dr. Lunine, I was particularly struck by your comment that a key issue is whether in a habitable environment life actually does develop, which is sort of the opposite of where we start. We started with the search, is there any life out there? And now it seems to me you're asking a very different question, which is we see a lot of components that we would think ought to lead to life. Does it lead to life or does it not? What are the technological breakthroughs you see us needing to support to answer that somewhat different question? It seems to me that's a different question than I certainly would have thought about 5 years ago.
Well, it's a different question, but it's a related question. We really have no laboratory model for how life began on the Earth. No one's done this in the laboratory. And so one of the reasons for going out to environments in our solar system where the conditions for life are apparently there and possible is to see whether life actually began, essentially to do the experiment in the field instead of in the laboratory. And the critical things we need for that are devices to analyze abundances of amino acids, fatty acids, to look for patterns in other molecules that might be part of an exotic biochemistry, for example, on Titan. Part of the problem is that it's not entirely clear what we want to look for in some environments. In other environments, like Mars, Europa, and Enceladus, it's very clear what we want to look for. So chemical analysis is critical, and the ability to get out to these planets and sample planets and moons and sample them is also critical.
Thank you. And if we might be able to follow up afterwards with some more detail, because again, our job is in part to try to set funding priorities, and they need to take into account these changes. So I think, Dr. Stofan, your comments about the near surface presence of water compared with, say, Europa, where it's so deep and that presents harder technological challenges, may help guide us with the, as I'm afraid we have to say, the not enough money that we have to do this research. I wish we had more, but with what we have, we want to make sure it has the most impact and rely on your judgment in guiding us. Thank you all very much.
And thank you, Ms. Esty. The gentleman from Louisiana, Mr. Abraham, is recognized.
Thank you, Mr. Chairman. I'm one of those teenagers that rushed home to see the original Star Trek with William Shatner and Leonard Nimoy. So this is fascinating, and like the chairman said, we have a million questions. I'll ask a couple. Dr. Stefan, like you, I'm of the opinion you're going to have boots on the ground, so to speak, to finally answer the question. So let's bring it a little closer to home. You referenced the possible meteor or asteroid in the Antarctica. I'm assuming you're referencing the Allen Hills meteor back in, what, 84, I think it was when it was discovered. And if we go to a synthetic biology topic such as XNA as opposed to DNA, RNA, would our funding be more appropriate in a realistic term as to funding projects in that realm as opposed to, something that may be 100 years off as far as time travel or space travel is concerned?
Well, I certainly think that this is as I said, it's so interdisciplinary that you really need a multi-pronged approach. And so I think that's what NASA has developed by saying we do need boots on the ground. I personally think it's achievable that we meet the president's goal of getting humans in the Mars vicinity in the 2030s. I think it's completely doable. And in the meantime, of course, continuing our robotic exploration like we're doing with the Mars 2020, moving with the Europa mission to go and explore Europa. So I don't think it's an either or, I think it's an and. We need to do the technology research here on the ground. We need to do biological research, and certainly synthetic biology is an amazing expanding field at this point in time. But I think it's all of those things together that help us move forward scientifically and help us refine the scientific questions as we move forward.
And you've got DARPA, you've got USARMed, you've got NASA, you've got all these agencies looking for other life forms, doing research on genetic engineering, those types of deals. Is there any one agency that is spearheading or that these other agencies report to? Is there any herding of the cats, so to speak, where this research can come under one big umbrella and people talk to other agencies and actually come up with some formulations?
Well, I think in the area of astrobiology, this is why community roadmaps, like the Astrobiology Community Roadmap that is coming out this year, because in my mind, going to the community, whether it's through the decadal survey process, through the academies, the Astrobiology Roadmap is going out to the community who, in general, the scientists know where all the funding streams are coming from. They're the ones who are truly pulling and doing this multidisciplinary work. So when you get the community together and say, here are the priorities, here are the areas that we think have the most potential for advancement in the next 5 to 10 years, it's that voice of the scientific community that I think helps guide it.
But is there a one voice at this point, or is anybody at the top of the heap, so to speak?
In astrobiology, I would argue that NASA is really guiding what we're doing and what the next steps are. We certainly work closely with other agencies, though.
Does NASA have any rules or regulations that they foresee that would limit or harness this potential breakthrough? I mean, I could see where with what we have available even now with some of the generic engineering that, you know, some of this stuff could turn out to be kind of bad stuff.
We certainly don't have any regulatory authority, but I'd have to take that question for the record because I don't know the answer to it.
Okay, thank you. Dr. Lynn, just a quick comment on what you had spoken with the congressman earlier about potential life developing in an environment. Just a personal question, what is your theory on panspermia, the bringing of life forms into our Earth atmosphere on an asteroid or a meteor?
I think that panspermia has occurred, certainly between the Earth and Mars. We know that materials are exchanged between those two planets. We have the Allen Hills meteorite, and there are some good studies that have been done that show that amino acids will survive the trip to the Earth through the atmosphere on an asteroid, and possibly bacteria as well. So there may well have been extensive exchange of life and biological materials between the Earth and Mars, particularly in the early history of the solar system when impacts were more frequent.
Okay, thank you, Mr. Chairman. I'll yield back.
Thank you, Mr. Abraham. The gentleman from Virginia, Mr. Byers, recognized.
Thank you, Mr. Chairman, and thank all of you for coming today. It's a fascinating hearing. Mr. Chairman, thank you very much for structuring this. And I look forward to our Science, Space, and Technology CODEL to low Earth orbit, which I'm counting on you to do this. To go quickly, Dr. Simeon, you know, for years we had the PCs at our home following SETI doing the analysis of the work, and it was fun. We have no successful conclusion yet. I'm fascinated by the $100 million for the breakthrough project. But what happens when we discover extraterrestrial intelligence? Do we have a plan about what happens next?
Well, I'll just mention that so SETI at Home, the program on PCs, is still around, and you're all welcome to download it. It runs on cellular telephones now, as well as home PCs. I think a lot of people have put a lot of thought into what to do when we potentially eventually discover intelligent life or any kind of life beyond the Earth. I think there will be a range of reactions. I think for my part, my personal opinion is that probably the most common reaction will sort of be, I told you so. I think many people probably believe that the life is out there and maybe even intelligent life, and certainly the more we learn about the exoplanet population and water on Mars and these kinds of things, I think reinforce with people the possibility. But the truth is that we really don't know for now, and I think to see what the reaction will actually be, we'll probably have to wait and see.
It'd be interesting to have protocols in place for when we finally get the breakthrough, what do we say back and the like, so, yeah. And Dr. Lenine, you talked about Titan and all the methane and ethane and all that, and I sort of basically understand that most elements only come from the explosion of stars, so you'll get the carbon. But are methane and ethane, can they develop other than biologically?
Yes, actually, methane is a very simple organic molecule, and so it occurs in many environments, in interstellar clouds, it's there in comets, it's measured there. And so these are evidently sources of methane that are not from biology. It's simple to make in the laboratory, for example, and carbon's very abundant, as you alluded to, as one of the products of stellar nucleosynthesis. So we think that Titan has an enormous inventory of methane that is not biological, that was produced by abiotic sources. And the ethane that is also part of that system was produced from the methane, and that's something that Cassini has confirmed for us by measuring the places in the atmosphere where the ethane is produced from the methane by ultraviolet chemistry. Okay. So Titan is a huge repository of abiotic methane. Now, from those and other organic molecules, does some form of life occur on the surface or arise in the seas of Titan? That's the part we don't know.
Great, thank you. Dr. Stofan, I think this is for you, but maybe Dr. Lenine. Dr. Abraham talked about the panspermia. And I know there was a project that evolved out of Harvard, MIT a few years ago, trying to replicate the early origin of life on Earth, the primordial soup, organic soup thing. Is there much evidence or any evidence that life on Earth may have started someplace else?
You know, we just don't know the answer to that. You know, we know what we do know is that life evolved very rapidly here on Earth after conditions stabilized. And again, that's a factor that makes us optimistic that there's life elsewhere in the solar system, knowing that life arose relatively rapidly here. But we honestly don't know if, again, did Mars, you know, bacteria come from Mars, bacteria from Earth go to Mars? We just don't know that, and that's why it's so critical, we think, to continue this search for life on Mars, the other bodies of our solar system, to answer that very question.
Great, thank you. And Dr. Bean, it's fascinating, your photos of Enceladus and the fissure, and I was trying to, if you could go a little deeper on, are those gases that are being released through the fissure that?
Right. So I think that would be more appropriate addressed to Dr. Lenine, if you want to.
Okay. Was that, I'm sorry.
Yeah, that's okay. I think it was my slide. So,
okay, great.
In the case of Enceladus, those fissures at the South Pole have jets of gas and ice emanating from them, and those jets merge to make this very large plume that was discovered by Cassini. We did not know of the existence of this plume until the Cassini mission, and once the plume was discovered, Cassini was directed to actually fly through the plume multiple times and sample the material in the plume with its instruments. One of the important lessons that we get from this is that these flagship missions with large numbers of instruments are able to respond very flexibly to new discoveries. The instruments that actually tasted the material in the plume were designed to sample the atmosphere of Titan. But once the plume was discovered, Cassini could actually use those same instruments to tell us what the plume is made of.
Great. Thank you very much. Chair, I yield back. Thank you.
Thank you, Mr. Byer. The gentleman from Florida, Mr. Posey, is recognized.
Thank you, Mr. Chairman, and thank the witnesses for their testimony today. I just wonder if each of you would give me your definition of life.
I think it's something the scientific community really struggles with. You know, certainly there are signs that everybody agrees on, you know, something that is self-replicating, something that consumes something and excretes something else. But the problem is life here on Earth, what we've learned from doing research here on Earth is that life and the boundary of what's not life and what is life is a little blurry. And that's why this is going to be so challenging to go find life on other planets.
Life is a self-replicating system that undergoes evolution or mutation and which also seeks to minimize its local entropy, maximize its order, in the sense that chemically we use a very small fraction of the possible compounds that can be produced from carbon. And the fact that we're alive is because we can take in large amounts of nutrients, process them to make this very small specific set of molecules that build our structure, control energy in and out, control the information needed to build these other molecules, and then we expel the rest. So for me, with my physics background, it's very high order, very low entropy in a chemical system.
Thank you.
I would say that astronomers use a very basic definition of life because the information that we can get when we study the atmospheres of exoplanets will also be very basic. And so we use a very Earth-centric, even human-centric point of view for life. And that's the thing that we're looking for evidence for in the atmospheres of other worlds.
I guess there's some advantage to going last on a question like that. I don't know that I have a lot to add to what Dr. Stefan, Lenine, and Bean said. I certainly appreciate the thermodynamic definition of life that Dr. Lenine articulated. I guess maybe the only thing that I would add to that is that I think many of us in the astrobiology community assume that life is something that we'll know when we see it. And hopefully that's true, but we're not sure. And it's quite possible that the first life that we encounter beyond the Earth will be very different than any kind of life that we have on Earth.
Thank you. If you, each of you, the questions for each of you, if you could pick a mission, just personally say, I want a mission that will do this, achieve this, you know, what particular type of mission would you choose?
You know, I'm going to go with geologists on the surface of Mars, looking, you know, cracking open lots of rocks, looking for life. That's my big payoff mission.
So I would go with the Europa mission, and the reason for that is we have so much tantalizing evidence that Europa is a habitable environment, but there are missing pieces, including whether there are organics and where to actually go search for life. And I personally, and I think we have been waiting since 1998 for a mission to follow up on the Galileo orbiter discovery of the ocean under Europa. And so from my point of view, it's a critical mission to do, and I would make that my #1 right now.
So I would like to see a large space telescope that can take spectra of other Earth-like planets orbiting nearby stars, something very similar to the previously proposed and discussed Terrestrial Planet Finder mission, or TPF, which you may have heard about. I think the advantage of studying extrasolar planets is that we have a chance to look for, to do an experiment, so to say, on how life arises on terrestrial planets in a variety of environments. And so that's what I would like to see.
I'm not sure what list I'm choosing from here, but as a radio astronomer and someone interested in SETI, I think I'd be remiss to not suggest that it would be wonderful to put a radio telescope on the far side of the moon. That region of the moon is protected from radio frequency interference from the Earth, something that confuses us in SETI experiments and allows us to observe at very, very low frequencies very effectively.
Y'all make the choices really tough, don't you? Following up on the last answer, some people think because we've been to the moon, we shouldn't return to the moon. There's obviously some strategic reasons for going there for future transportation as a stepping stone to Mars, but I'd like to ask each of you your opinion of whether or not we still have a lot to learn from our own moon.
I chaired the Interplanets panel for the last Planetary Science Decadal Survey, and listed in the New Frontiers class of missions is a mission to look at the terrain around the South Pole of the moon, where we think the lunar mantle has come very close to the surface, to help us understand the origin of the moon and what that tells us about the origin and evolution of our own planet. So scientifically, we certainly have lots of outstanding questions about the moon that the scientific community has articulated through the decadal surveys.
The moon contains the geologic record of the first billion years of the history of the Earth, and that record has been more or less lost on the Earth because the Earth has been so active. And so that is, for me, the critical aspect of the scientific value of the moon. That's the time when life began on Earth, and to understand what was happening geologically, we can do no better than turn to the moon.
I'd like to answer the question in terms of human spaceflight. Dr. Stofan and Dr. Lenine gave great scientific answers, but for me, if we can combine science with a human element, I think that's a very powerful thing. That'll reach out to the public, that'll excite our school children to follow math and science, and so for me, that's an exciting yes to that question.
I think I would agree with Dr. Bean. I think a manned mission to the moon would be a wonderful stepping stone to future missions to perhaps Mars.
I want to thank you all again for your testimony. It's really been wonderful, and I think everyone enjoyed it. Thank you, Mr. Chairman.
Thank you, Mr. Posey. The gentleman from California, Mr. Bear, is recognized for his questions.
Thank you, Chairman and Ranking Member. And I really want to thank both the Chairman and Ranking Member for this this topic. You know, it comes at a very timely time, and the witnesses. You know, as a child growing up in Southern California, at the heart of the aerospace industry in the 60s and 70s, you know, the space race captivated us. The Apollo missions, Apollo-Soyuz, Skylab, you know, going to the space shuttle. And, you know, as someone who went into the sciences and became a doctor, you know, it really was pivotal in, you know, fostering our curiosity. I mean, if we think about who we are as a race, as human beings, we are naturally curious. We are natural explorers, and we want to find those answers. And I think it's incredibly important, the work that NASA is doing, the work that our scientists are doing in fostering the imagination of the next generation. And I think we need to do more of that, in fact, because, you know, in listening to some of your testimony as well as how you answer the questions, we don't know what life is going to look like. We don't know what we are going to discover. We don't know what frequencies we should be listening for. But we do know that something is out there. And if we don't, continue to push our imagination, if we don't continue to, we don't know how we're going to get to Mars, let alone how we're going to send a human being to Mars and bring them back. But we do know if we challenge ourselves, we will discover that. We always have. And I think that is the importance of what we're doing here on the Science and Technology Committee, but also in Congress and also working with our colleagues around this world, because this is not just a U.S. mission, it is a human mission to find and discover, where we came from, how life evolves, but also how life becomes extinct as well, as we're looking at these planets, the impacts of those discoveries on what is affecting our own planet right now as we deal with climate change, as we deal with a changing atmosphere. Those discoveries will help us manage our own issues on our planet. I'll ask a quick question of each of the panelists, and each of you can answer this. In explaining why it is important to search for life beyond our planet, beyond just the philosophical elements, if you were to explain this to an elementary school student or the public in general, how might you put why this is such an important endeavor? And we'll start with Dr. Stofan.
I certainly always mention this fact that ever since I think there have been people looking up at the sky, we've wondered, are we alone? And so there is that huge philosophical piece. But the other piece I like to talk about is, when we find life, does it have RNA? Does it have DNA? Is it cell structure like our cell structure? And then how can we take that information and look back at life here on Earth and try to understand better how life here evolved, what the conditions are? And so to me, you do get a tremendous learning about life in general by finding life on other planets. Obviously, also, I try to point out to audiences, if they don't buy the science and the philosophy stuff, I try to point out to them that when we do great human endeavors, whether it's, exploring the moon, building the next great telescope, we challenge technology. We bring good technology jobs to this country. We move this country forward in our reputation, both internationally and at home. And I think there's that inspiration part of just doing really hard things, accomplishing great things, which this country has demonstrated so ably that we're so capable of. And I will say, I also like to tell school children when I go and talk to them, I say, oh my gosh, you guys have so much work to do. We have 5,000 planets we need you to go study. We've got entry, descent, and landing for humans on Mars. You guys better grow up and get to work. We need help.
Right. This might be a philosophical answer, so I apologize for violating the ground rule. But, for the last 500 years, we've lived in a kind of a Copernican worldview where the Earth was not the center of the universe or even the solar system. It's a planet in the solar system. The sun is not at the center of the galaxy. It's just a common star in the galaxy. The galaxy is one of hundreds of billions of galaxies in the cosmos, and yet we are singular. I mean, life and intelligent life and ourselves, at the moment, we know of no other form of life, intelligent life, and the Copernican worldview would say they're all over the place. And it's crucial to test that, because if that turns out not to be the case, that's going to shatter our worldview.
So my answer would be more along the lines, of course, those are excellent reasons why we want to do that, and finding out the answer would be absolutely fascinating and change our worldview. But I think also the process of doing it tells us a lot about ourselves, tells us about our hopes and dreams, and about how we can work together as a country and as a society and in the world. So for me, I want to emphasize the process of looking for that answer, whatever the answer may be, if it's a positive or a negative. But the process, through the process, we find out a lot about ourselves.
So I may be a bit biased, but I think that life is the most interesting property of the universe. The idea that somehow in this largely mechanical universe that we live in, that we understand to great detail, some sort of an organism came to be that could question its own existence, that could wonder about the universe itself and where it came from. if we don't understand that, then I think we don't understand perhaps one of the most fundamental properties of the universe that we live in, and so we must answer that question.
Great, thank you.
Thank you, Dr. Barron. Just to follow up on that question, if other members will allow me, just real quickly, yes or no, do you think intelligent life does exist elsewhere in the universe? Dr. Stofan?
Maybe.
Okay, Dr. Lunine.
Mr. Chairman, am I allowed to answer by saying I honestly don't know?
No, that's a legitimate answer. Members of Congress should give that more often themselves, by the Dr. Bean.
I don't know either.
And Dr. Simeon. I'm not asking you if you know, I'm just asking you if you think.
I also don't know, but I think it would be incredibly strange if we were the only example of intelligent life in the universe. And I'll quote Stephen Hawking just very, very briefly, someone much smarter than I am. A universe in which intelligent life only exists in one place and a universe in which intelligent life potentially exists in many, many places are very, very different places.
Very good. Thank you, Dr. Simeon. We'll go now to the gentleman from California, Mr. Swalwell, for his questions.
Thank you, Chair, and thank you to our panelists. Congratulations. I have to say it's refreshing to have a hearing about something so big, so exciting, and farther than the eye can see. And so, in Washington, it gets quite frustrating here. It feels like we are so focused on just very small, incremental things, and people at home get quite frustrated that seems to rule the day here. But the work that you're doing is so important, so big, and will inspire so many future scientists. So congratulations. I had the opportunity to go with the chairman and a few others to Antarctica. One of your colleagues, John Gunderson, joined us on that trip, and he told us as we went through the McMurdo dry valleys that that area, and he was excited to be on that trip and visit that area because it most closely resembled what we believe many of the parts of Mars to be. And so this discovery is another step forward in that effort. As far as the water that has been discovered, do we believe it could support life? Is it too salty? Do we know enough about its properties to make that conclusion yet? Dr. Stofan?
It certainly makes us concerned that water in particular had a lot of perchlorates in it and salts, and so based on and this is where everything we say, based on what we know about life on Earth, that would not be a very habitable type of water. That being said, what we know about the Earth is like this. What could be is like that. So fundamentally, we don't know.
Any other thoughts from the panelists on that question?
Well, just very briefly, if I talk about the possibility of looking for exotic biochemistries on Titan, I'd better not say that life is impossible in the perchlorate solutions on Mars, which would be a lot easier to imagine the biochemistry. So yes, terrestrial life as we know it, bacteria, et cetera, would all be sterilized by that solution, but is there a form of life that has evolved to live in that solution? That would be very interesting, but not impossible.
And speaking of sterilizing, according to the New York Times, NASA has no plans to examine closely any of these places which may contain water or could be potentially habitable places out of fear of contaminating them with Earth's microbes. So sterilizing probes is expensive. Do you think it's time to re-examine this approach so we can follow up on this latest discovery?
I think the scientific community right now, not just in the United States, but around the world is, because obviously planetary protection is something that's governed by international policies and procedures. We want to make sure that if we find life on Mars, we know we've found life that is Martian life, not contamination we brought from the Earth. And so certainly in areas where there are water, we need to be cautious, extremely cautious, as we move towards exploring them. However, those areas could potentially be the most interesting areas to explore. And so I think the scientific community is certainly going through a process right now of saying, okay, right now we don't think that's the place to run to and potentially contaminate, so let's take a really measured, very scientific approach to how we might get at exploring those regions. Obviously, when we eventually send humans to Mars, that's going to lead to much likely broader scale contamination. And so I think it's important as we lead up to sending humans to Mars, we try to keep Mars as pristine as we can.
Great. And finally, 38 million Californians are wondering, can we get that water to California?
Certainly the California drought is something that NASA is very concerned about. We've been using our satellites to do what we can to help to certainly monitor with the GRACE data. We've certainly seen the alarming reduction in the amount of water in the aquifers. We've been working on some projects with farmers in California that have, in some pilot projects, have reduced water usage by as much as 30%. So NASA is trying to help.
That's great. Thank you. Yield back. Thank you, Chair.
Thank you, Mr. Swalwell. The gentlewoman from Maryland, the ranking member of the Space Subcommittee, is recognized for her questions.
Thank you very much, Mr. Chairman, and thank you to the members. I was sort of curious, I don't know if Mr. Foster had a chance, but we were kind of speculating over here as to whether there's value in doing the kind of marking of all of these different sources to determine whether there was at some point just sort of one general dispersion so that there's a relationship between potential life that we might detect one place and another. And so I don't know if that kind of work is going on, and I wondered, Dr. Lamine, if you could speak to that.
Sure, I'd be happy to. I assume you're talking about in our solar system.
Yes.
So there's been quite a lot of work done, of course, to understand how frequently material has been exchanged between the Earth and Mars, as I alluded to, but also for Europa. Is it possible to get material from Europa to the Earth and vice versa, and then Enceladus and Titan? And the answer is that the farther out you go, the less likely it is. So the most recent studies that have been done, which are all computer models, say that the chance of cross-contamination between the Saturn system and the Earth is very, very small. And the chance of contamination between Europa and the Earth is a little bit higher, but it's still relatively small. So one of the advantages of going to the outer solar system, in addition to exploring Mars, is that we may be going to habitable environments which have not been contaminated by either the Earth or Mars. And so if we find life there, or the signs of life, we have somewhat higher assurance that that life had an independent origin of life on Earth, which of course is one of the important questions. Could life have begun more than once in our own solar system? And that's one of the attractions of going to the outer solar system.
So then that leads me to another question, Dr. Lamine and Dr. Bean. In a 2007 National Academy's report called The Limits of Organic Life in Planetary Systems, there was a caution against searching for a model of life that's based on the model that we know here on Earth, and a conclusion that life is possible in forms different from those on Earth. And so I wonder if you could talk to me about the recommendations that came from the report to further inform investigations to detect and identify possible forms of life in other planetary environments. And I think, Dr. Lunine, in your testimony, in your prepared statement, you asked whether the seas of Titan should be included in our search for life because of Titan's use of methane as a working fluid in place of water. So I guess my question is, to what extent would missions to Titan and other potentially habitable environments be able to investigate habitats of life forms that are different, that may be different from those on Earth?
So the 2007 report came out very strongly in favor, as you noted, of looking at environments that had the general conditions for habitability: energy, liquid, organic molecules, and that if in fact those environments were found not to have a form of life, that would tell us that there's something indeed very special about liquid water. And so that was, I think, one of the recommendations, as I recall, of that report. The challenge, of course, is how to look for biochemistry in a methane-ethane liquid. What do we actually look for? There's no guideline that terrestrial biology gives us, except for the guideline that life will be very selective in the chemical compounds that it uses for catalysts, for building structures, and so on. And so therefore, if we go back to Titan, for example, with a boat or a submarine or whatever to explore these seas, if we find that the organic molecules in the seas are just like what's in the atmosphere, basically everything, that's not going to be very promising in terms of life. But if there's a suite of particular molecules and structures that are made over and over again, then that might suggest that if not life itself, at least a chemical evolution toward life is happening in those seas. Beyond that, it's hard to say very much because we have our one example of life on the Earth. Now, just very briefly, in places like Enceladus and Europa, which have very Earth-like environments, we would expect that many of the basic molecules that terrestrial life uses, like amino acids, which are abundant in the cosmos, that we would see that in life in those environments.
Dr. Bean, in the time remaining.
Right. In the context of the search for life on extrasolar planets, astronomy, my field, is a very discovery-driven field. We want to build space telescopes and instruments that are designed to be able to answer a question, and we inform, the design of those instruments with what we know about on Earth. But we also know that we're going to find unexpected things. And so we want to have as flexible instruments as possible, and we want to make as complete characterization of these planets as we can. Just to give you an example, the Hubble Space Telescope and the Spitzer Space Telescopes were never designed to look in the atmospheres of extrasolar planets, but that has become one of the most impactful things that those telescopes have done, just because they were built with a suite of instruments that were very flexible. And so we have to benchmark our design for these instruments based on what we know, and what we know is limited to the Earth, but we also want to remain open-minded and flexible and do this complete characterization of the planets to try to answer this question in as holistic a way as possible.
And I've greatly exceeded my time.
Thank you, Ms. Edwards. The gentleman from Colorado is recognized for his questions, not with trepidation, but with curiosity and expectation, because I'm never sure where he's going to go with his questions, but he is recognized.
And Mr. Chairman, and to the ranking member, I've served on a lot of committees in the Congress, and this committee is by far the most exciting, stimulating, energizing committee in the Congress. And as I'm sitting down here and looking up at the top row and reading Tennyson, "For I dipped into the future, far as human eyes could see, saw the vision of the world and all the wonder that would be." Listening to you all, that's what this is about. This gives me goosebumps, the versatility of your instruments or your minds to say, you know what, this was really intended to do that, but we could use it for this. And I just enjoy this committee so. And Dr. Barra talked about the challenge and the desire of all of us to explore. I mean, I have some differences with the chairman on prioritizing and actually funding, because I see what you all do in your research and your service to be investments in the future, and that will pay for a long time to come. And I don't think it's a zero-sum game pitting the astronomers against the physicists and all of that stuff. And I don't think the chairman does either, but I really would like to see us move forward, obviously, with the Orion project and get humans to Mars. And with that, I'm going to yield to my friend from Maryland for her questions.
And I thank the gentleman from Colorado. We pulled a fast one on the chairman there. Dr. Stofan, I just had one question about how you're planning to use the astrology roadmap that's going to be released later this year and a year later than initially thought. Will it be a major vehicle that NASA is going to use to establish priorities? And then what kind of challenges did the agency face that caused a one-year delay to the issuance of the roadmap?
The astrobiology roadmap, that again, it will come out shortly. The reason that it's taken longer is because this science is evolving so rapidly, and how the scientific community looks at it, bringing in all these multiple disciplines that want to have a voice in astrobiology, because you might have thought 10 years ago, if you're a heliophysicist, that nothing you do has anything to do with astrobiology. All of a sudden you say, wait, I can actually contribute. And so that's been the reason for the delay of the roadmap, is we've just been trying to get the best science from the scientific community, get it properly reviewed, and get it out as soon as we can. And so we're happy that it's done, and it's about ready to go. How we use those roadmaps is definitely comes in several different ways. Basically, when anybody then proposes to NASA, whether it's to do research, to do a mission, they then say, here's how my mission that I'm proposing maybe to a competitive line at NASA, here's how I'm consistent with the goals of what the community is saying. And then we can use that at NASA and say, is this really high priority? Because we look to the community through these community roadmaps, through the decadal process to say, what is the best science? What's the latest science, the most up-to-date science? And then how can we use that to inform our decision makings?
So just really quickly, is there a plan to have the National Academies review the roadmap as well?
I don't know that. I can take that for the record.
All right. And with that, I will yield back to the gentleman from Colorado and just say I do get a little bit concerned with these, constant discoveries, which are really great and we find incredibly fascinating, that the public then becomes numb to it in a way that would harm us in terms of making sure that you have the resources that you need. And with that, I yield back to the gentleman from Colorado. Thank you.
And to the chairman and the ranking member, the thing that I enjoy about this is we are looking so forward and towards the future. And tonight, I don't know if you talked about The Martian or not, but the thing that is so fun about that book, one, he's a wise guy, and two, in that book, it's about problem solving. Whether it's math or engineering or physics or biology. And that's what is so enjoyable about this committee and about the panels that come and speak to us. Because I see you all as looking to the future and solving problems. And I just thank you for that. And I thank the chairman and the ranking member for this committee because it gives me energy every time I come in here.
Thank you, Mr. Perlmutter. You actually beat me in quoting Alfred Lord Tennyson because I was going to end by doing that. However, just to add one more tidbit of information here, this quote that you see behind us on the wall is from a poem called Locksley Hall, and of course written by Alfred Lord Tennyson, who lived from 1809 to 1892. I have the entire poem right here. It's multiple pages, but that is a wonderful excerpt of it. That brings us to the end of our hearing, which was obviously informative and exciting to all of us. And let me just simply add that when we think that we're somehow limited in what we might explore or what we might detect elsewhere in the cosmos, I think it's helpful to remember that we here in the United States went from the Wright brothers to Apollo in 66 years. In 1903, we had the Wright brothers. We had two guys flying a contraption a couple of 100 feet, 20 feet above the ground. 66 years later, we had 12 people walking on the moon over several years. And any country that can do that can certainly continue to explore and learn from that exploration, and who knows, maybe even detect some form of life elsewhere. So thank you all for being here. Most enjoyable hearing, and I thank the members who are here as well. And we stand adjourned. Okay. Okay. We will miss you. I'm trying to get to both. I'm going to go to the reception for those two, and then I'm going to go to the meeting. But I was trying to figure out.
Make a presentation at that, and it's
They
right
didn't-
in the middle of the
See, they didn't ask me to do anything, so I'm going to do
Yeah.
I think that went well. I do too. Thank you. I'm going to go thank them. 106 lie within the habitable zone of the stars they orbit, where water could exist, and 14 are almost the size of the Earth. Whether life exists beyond Earth, and if so, how humans can detect it, is a critical question. If definitive evidence of life is found, it may be the most significant scientific discovery in human history. The search for life in the universe is a priority of NASA and the U.S. scientific community. Seeking habitable planets is one of the 3 scientific objectives of the 2010 National Research Council Decadal Survey on Astronomy and Astrophysics. The United States pioneered the field of astrobiology and continues to lead the world in this type of research. Since the space program began, NASA has explored the cosmos for life beyond Earth and has conducted scientific research that investigates this possibility. NASA's astrobiology program continues these scientific endeavors to improve our understanding of biological, planetary, and cosmic phenomena. Just yesterday, NASA announced that it identified flowing briny water on Mars. This past April, NASA's chief scientist, Dr. Ellen Stofan, made global headlines with her prediction that, quote, "We are going to have strong indications of life beyond Earth in the next decade and definitive evidence within the next 20 to 30 years," end quote. And I'm glad that Dr. Stofan has joined us today. Within our solar system, the question of whether life exists or existed on Mars continues to capture the public imagination. In the past year, NASA's Curiosity rover made several major scientific discoveries relevant to the search for life on Mars. Curiosity measured a spike in levels of the organic chemical methane in the local atmosphere of its research site. It also detected other organic molecules in drill samples from a mudstone that once sat at the bottom of a lake. And Jupiter's moon, Europa, shows strong evidence of an ocean of liquid water beneath its surface, which could host conditions favorable to some form of life. NASA selected 9 science instruments for a future mission to Europa. 2 of them are from the Southwest Research Institute in San Antonio and 1 from the University of Texas in Austin. These instruments will help scientists investigate the chemical makeup of Europa's potentially habitable environment. Last July, astronomers, with the help of the Kepler Space Telescope, confirmed the discovery of Kepler 452b, the first near-Earth-sized planet in the habitable zone around a Sun-like star. This discovery marks another milestone in the journey to find The Committee on Science, Space, and Technology will come to order. With that objection, the Chair is authorized to declare recesses of the committee at any time. Welcome to today's hearing, which is called Astrobiology and the Search for Life Beyond Earth in the Next Decade. Let me make a couple of announcements. One is an explanation, and that is to say that we expect more members shortly, but at least on the Republican side, all of our members are in a Republican conference that I left early in order to start on time here, but other members will be arriving shortly. And the same may be true of our colleagues on the other side of the aisle as well. We have a new member of the Science, Space, and Technology Committee, and I would like to introduce him. He is Darren LaHood, the first member to my left, whose father I served with in Congress some years ago. Darren LaHood represents a district in Illinois. He's a former state senator, or serving as a state senator when he was elected to Congress. Before that, he was both a state and federal prosecutor. So we welcome his many talents to the committee. He is going to be serving on 2 subcommittees, Research and Technology and Oversight, where he will be bringing all those legal skills to bear. And so we are pleased to have him join us today and permanently on this committee. And welcome, Darren, to you.
Thank you, Mr. Chairman.
I'm going to recognize myself for an opening statement, and then I'll recognize the ranking member. Edwin Hubble once said, "Equipped with his 5 senses, man explores the universe around him and calls the adventure science." There are few greater adventures than the search for life beyond Earth. When the Hubble Space Telescope was launched in 1990, planets around other stars had not yet been discovered. The only planets we knew were those that orbited our sun. Since 1995, however, when the first extrasolar planet was detected, the rate of discovery of new exoplanets and external solar systems has been truly remarkable. Today, with the Kepler telescope, we have found nearly 2,000 confirmed planets that orbit around other stars in our galaxy. Of these, 300 worked as an interdisciplinary scientist on the Cassini mission, which showed that one of Saturn's moons may host microbial life, and on the James Webb Space Telescope, which will study the origins of life in the near future. Dr. Lunine received his bachelor's degree in physics and astronomy from the University of Rochester and his master's and PhD in planetary science from the California Institute of Technology. Our third witness is Dr. Jacob Bean, Assistant Professor of Astronomy and Astrophysics at the University of Chicago. Dr. Bean also is the leader of the Bean Exoplanet Group, which uses telescopes to detect and characterize exoplanets. Dr. Bean's work has used the Hubble and Spitzer telescopes to make breakthroughs in astrobiology, which include the measurement of the first spectrum of a super-Earth planet. Dr. Bean also develops new instruments for exoplanet detection and characterization and is helping to design the giant Magellan telescope, which will soon be the world's largest telescope. Dr. Bean received his undergraduate degree in physics from the Georgia Institute of Technology and his PhD in astronomy from the University of Texas in Austin. Our final witness today is Dr. Andrew Simeon. Dr. Simeon is an astrophysicist at the University of California, Berkeley, and serves as director of the UC Berkeley Center for Search for Extraterrestrial Intelligence Research. Dr. Simeon's research interest includes studies of time-variable celestial phenomena, astronomical instrumentation, and SETI. And Dr. Simeon also is a leader of the Breakthrough Listen Initiative, a 10-year, $100 million initiative to search for extraterrestrial life that is possibly the most comprehensive search for alien communications to date. Dr. Simeon received his PhD in astrophysics from the University of California at Berkeley. We welcome you all. You're clearly experts in the field. And Dr. Stofan, will you begin?
Thank you. I'm pleased to appear before the committee to discuss astrobiology and the search for life beyond Earth. If I could have the first slide, please. NASA's science missions are providing strong evidence of possible habitable environments beyond Earth. With future technology and instruments currently under development, we will explore the solar system and beyond, and could indeed, perhaps in as little as 10 to 20 years, discover some form of life, past or present. Our search is making amazing progress. When I was a PhD student, scientists certainly suspected that planets might be commonplace in the universe, but we had not found evidence of a single one. 20 years ago, we found the first evidence of such a planet, and today, thanks to NASA's space missions and ground-based telescopes,
Will also take some time to discuss how their research activities can be used to help foster excitement in our young people and spur them to pursue careers in science, technology, engineering, and math. That's important because these young people are the future science and technological leaders and innovators who will be critical to our nation's growth and progress going forward. While it's exciting to search for intelligent life elsewhere in the universe, I hope we don't neglect nurturing the intelligent life we have right here in our country. As a final note, I want to recognize that this is a return visit by Dr. Lunine. 1 year ago, he and Governor Mitch McDaniels testified before the committee on their National Research Council's panel's report entitled Pathways to Exploration, a Review of the Future of Human Exploration, and that was completed pursuant to NASA Authorization Act of 2010. I highly recommend that our newer colleagues on the committee and in the rest of the Congress as a whole, for that matter, read this report, as I found it to be objective in its endorsement of the goal of sending humans to Mars and thoughtful in its recommendations for an exploration program to send humans to the surface of Mars. A central goal established by this committee in the House passed NASA Authorization Act of 2015. And with that, I again want to thank our witnesses, and I yield back.
Okay, I thank the ranking member for those nice comments. Let me introduce our witnesses. Our first witness is Dr. Ellen Stofan, NASA's chief scientist. She serves as principal advisor to NASA Administrator Charles Bolden on the agency's science programs and science-related strategic planning and investments. This is Dr. Stofan's second term at NASA, as she recently held a number of senior scientist positions at the Jet Propulsion Laboratory. Dr. Stofan is a recipient of the Presidential Early Career Award for Scientists and Engineers. She earned her bachelor's degree from William & Mary and her master's and doctorate degrees in geological sciences from Brown University. Our second witness today is Dr. Jonathan Lunine, the director of the Cornell Center for Astrophysics and Planetary Science at Cornell University, where he specializes in astrobiology. Dr. Lunine has extensive experience in the search for life on other planets. Another Earth. The Transiting Exoplanet Survey satellite, which will launch in 2017, and the James Webb Space Telescope, which will begin in 2018, will help scientists discover more planets with potential biosignatures in their atmospheres, such as evidence of oxygen and methane gas. Around the world, a relatively small number of astronomers monitor radio and optical emissions throughout the universe. They try to filter out the cosmic noise and interference of satellites and spacecraft to find anomalies that could represent life. The search for life beyond Earth also inspires a new generation of explorers. It motivates students to study math, science, engineering, and computer science. Just a few months ago, astronomers confirmed that Tom Wag, a 15-year-old student, discovered exoplanet WASP-142b, which orbits a star approximately 1,000 light-years away in the constellation Hydra. It is in our human nature to seek out the unknown and to discover the universe around us. The stars compel us to look upward and lead us from this world to another. Many Americans often gaze into the beauty of the night sky in awe. Some may wonder if there is life beyond our pale blue dot. I thank our witnesses and look forward to hearing their testimony today, and particularly about recent developments in the field of astrobiology and the search for life. And now we'll recognize the gentlewoman from Texas, Eddie Bernice Johnson, the ranking member, for her opening statement.
Thank you very much, Mr. Chairman, and good morning. And let me welcome our distinguished panel of witnesses today. I do look forward to your testimony. I want to welcome Ms. LaHood to the committee and simply say that the first week of this month, I visited the Curiosity team in France, and the excitement is beyond measure. Administrator Bolden stated in the preface of NASA's strategic plan that when we explore the solar system and the universe, we gain knowledge about the dynamics of the sun and the planetary system and whether we are alone. With respect to the question of whether we are alone, in search for life beyond Earth is a topic this committee has devoted a lot of attention to over the past 2 years. I don't know if we plan on taking up life somewhere else. I don't know where our chairman wants to go, but I'm interested in following him. I understand that the purpose of today's hearing is to get another update on that topic. It is my hope that our witness